Hello connections, welcome to a new video on electromagnetic fields. In the previous two videos, we have seen about the basic law that governs electrodynamic fields, and we have discussed about what is induced EMF and what are its types. In this video, we are going to discuss about an important topic, which is displacement current. So before getting into the displacement current topic, let's have a short recap about what is Ampere's law, because it is in connection to the upcoming topic. We know what is Ampere's law. So Ampere's law states that the flux density enclosed in a closed loop will be equal to the amount of direct current enclosed within that loop, right? So integral B dot ds is equal to mu naught I enclosed. So the amount of flux contained in a closed circuit will be equal to the amount of current flowing through the closed circuit, right? Now let's get into a case study. Observe a capacitor where you are charging it. Traditionally, the Ampere's law suggests that there is a magnetic field that exists around the wires in a closed loop. But what happens in the gap between the capacitor plates? We know that a parallel plate capacitor will have two plates in between a dielectric medium, right? So if the currents needs a complete path as per the Ampere law to flow, then a magnetic field is produced, right? But in case of a capacitor, the circuit is not closed. Then how does the magnetic field persist across this open circuit? That we are going to discuss in detail. And that current flow, or that continuity in current flow, is due to the concept called displacement current. Okay. So as per the original Ampere's law, it states that the magnetic field produces an electric current. It works perfectly for steady currents in closed loop. So that is mathematically expressed through B dot dl is equal to mu naught enclosed. But when dealing with time-varying electric fields like those in charging capacitors, this Ampere's law alone fails to maintain the current continuity across the open surface, because there is an open small gap in the capacitor, right? This led to Maxwell's to find the existence of displacement current. If the Ampere's law still holds good, then there must be a magnetic field generated by the changing electric field between the plates, right? So that induced magnetic flux field makes look like that there is a current. So if you observe this parallel plate, in between there is a gap, like in a capacitor. We know the current flow through the conductors. Okay, so the current enters the capacitor and it creates a magnetic field in the plate. But what happens in between the plate? There is a gap, a dielectric medium, right? So in that medium, due to the change in electric field between the plates, a magnetic field is induced in between the plate, which causes a current flow. And that current is called as the displacement current. So now let's get into the properties of displacement current. Between the plates, if the radius is very large, then the magnetic flux density would be identical to that at an equal distance from the wire. For the regions between the plates but the radius are less, then the I enclosed would be enough to determine the total current flowing through the plates, which is very uniform. So the equation for displacement current is that ID is equal to epsilon naught d phi E by dt, because this displacement current is a result of change in electric flux. So ID is proportional to the rate of change of electric flux with respect to time. So now we remodify the Ampere's law with Maxwell's hypothesis, thereby obtaining Ampere-Maxwell's law, which states that integral B dot ds is equal to mu naught I enclosed plus the displacement current, which is mu naught I d enclosed. Now substitute the value for ID enclosed. So therefore integral B dot ds is equal to mu naught I enclosed plus mu naught epsilon naught d phi E by dt. Okay, so this simple concept is applicable only for the capacitors where the Ampere's law fails to hold good. So in today's topic we have discussed about displacement current with its basic equations of Ampere's law, and then we discussed with the capacitor charging, and then finally we gave the definition for the displacement current, which is the actual which plays an actual role in the capacitor. And we have discussed about displacement current and then the properties of displacement current between the plates, and finally we concluded with the modified Ampere Maxwell's law. So thanks for listening. In this video we have deeply discussed about the displacement current concept. In the next video we will discuss another new topic in electromagnetic field. Thanks for listening.